everyone. Happy Saturday. Thanks for joining us again for another MICCAI RISE seminar. So today we have Akash Awasthi, who is gonna talk about agentic AI for radiology education. Akash is a machine learning engineer, researcher at University of Houston and also at the NASA Ames. His research focuses on developing collaborative AI systems using large language models for healthcare education and decision support. Uh, yeah, take it away, Akash.
Thank you. Thank you so much, Pulkit, for the great introduction. So can you hear me right? I'm audible well enough.
Yeah, perfect.
Okay, sure. So hello everybody. Good morning. So today I'll be presenting about one of my important work during my PhD, agentic AI for radiology education. So let's get started. So a bit about myself. I am the research which I'm going to present today was funded by NIH at University of Houston, and we had a lot of collaborations with MD Anderson Cancer Center and University of Arkansas. And I'm also a research scientist, incoming AI research scientist, as was introduced at NASA Ames Research Center in Mountain View, California, where I lead the build structure mapping product or efforts of NASA in machine intelligence group. So let's move on to the discussion we are going to have today. So the agenda for the meeting, agenda for the today's talk is going to be, first time we'll be discussing about the radiology, challenges in radiology, some of the how we can use AI for radiology education, and then because education is important so that we can reduce the radiology errors, so that's also we're going to discuss about, and then going to discuss about the reasoning behind the errors, how we can develop such systems which can basically also give a reasoning why those errors happen, because that is important for the radiology education. Then we have also developed a system actually which is going to be released by RSNA soon, but I will be showing the system, how we can have AI system, like a kind of an AI system developed we have for radiology education, giving a personalized feedback. So a quick about the radiology. Let's talk about what the radiology is, specifically detecting, diagnosing, and monitoring of the disease. And radiologists usually deal with the CT scan and chest X-rays and MRIs and radiology report. So, but in my talk, in the current presentation, I will be focusing more on the most of the work is on chest X-rays. We plan to extend it to further modalities, but the most is around chest X-rays. So most of important challenges in radiology basically are teaching or training gap, because radiologists doesn't have much time. Radiologists do not have much time to really teach the students. So and also give him like a personalized mentorship, personalized feedback that they should be diagnosing the image or CT or MRI in a certain way. So they basically don't have that much of time because of the clinical workload. Another problem is the diagnostic error, which is like making missing the diagnosis or doing the incorrect diagnosis. And you can see that the both of these challenges which I'm talking about are interrelated. So if the teaching if the radiologist or resident is not well trained enough, they may make more errors, or the vice versa. So you can see that the radiology education is very important to make sure that the residents or the further radiologists are have a better way of diagnosing the disease or diagnosing the pathology. So let's talk about how this radiology, how AI is basically used in radiology education so far, because people have used artificial intelligence for radiology education, specifically curriculum development, for teaching and learning, And for learner assessment, so people have been using LLMs to do generate those kind of a content and everything for the radiology student. But really, there has been very few or very less, I would say, efforts on the personalized radiology education side. Basically, can we develop the system which can give a personalized feedback to the radiologist, to the residents, or the um, uh, resident or the radiologist, basically medical student. So can we have a system which can take this, the diagnosis, or the student or residents, and can give a personalized feedback to them that, oh, you missed this portion of the the image, or you did not diagnose it, or you need to do better, which is like very much related to the way they diagnose the CXR image. So it's like more related to their cognitive processes. So can we have an AI system which can give personalized feedback based on their cognition of diagnosing the CXR image, specifically for other modalities as well, but current work is focused on the CXR. So as you can see that I show here, that this kind of system we envision, which takes the report and CXR, and how we basically know the cognition of a student, how did he navigated the image, is basically through the eye gaze data. So we have an eye gaze data, and we have an image and report, and we input to the, can we develop a simple agent or something which can give a personalized feedback that, oh, you missed this subtle pulmonary opacity, and you should, because you did not had enough visual attention for enough time, you did not focus, so that's why you miss it. So this kind of a personal feedback are very important sometimes for the residents to change their navigation style, or give more importance, or they have to learn. So yeah, so these kind of systems are missing, and in this work we are trying to develop those kind of agentic systems which can give a personalized feedback, and can lead to a personalized radiology education based systems. So let's talk about as I said, that if you want to have those systems, the most important thing is we need to they should be able to give feedback about the errors radiologists make. So what kind of errors, basically, if we want to develop those AI agentic system, we need to basically have those systems. We need to have those systems with the capability of detecting and correcting and reasoning around those errors. So first, let's talk about what kind of errors happens in the radiology, specifically the two types of error: interpretive errors, the perceptual error and cognitive error, and there is a non-interpretive errors. So which is basically technical communication workflow, basically about they make some mistake in communication, or writing or grammar and all of that stuff. So that is something people have already working on it, kind of error, system based errors. But the important errors, if we want to give a capability to an agent to correct the errors, the important part, the errors which takes most of the percentage, is perceptual errors, which is basically they did not see for enough time, or they did not focus on the region, or they miss it. So here I show an example of the error, perceptual error, how it can be. So you can see this CXR image, and there is I just overlaid the fixation of eye gaze fixation points, and this is the report from the student and teacher. So this is the correct version. Let's consider this the correct version of the report, and the the CXR image, and the eye gaze overlaid, and this is the erroneous version, where you can see the right effusion is masked or not there. He missed it, student missed it, and this is due to basically the due to the less attention, or the fixation duration. If you see this area was not focused well enough. So this is basically an idea of perceptual error. So if you want to have that kind of ability to an agent where it can give a personalized feedback, we need to also make sure that the system can understand the error and understand the eye gaze data and the report, and can do a kind of multimodal reasoning to give them the region of the error. So why perceptual errors basically happen? So there are three. I mean, there are many regions for perceptual errors. They can be imaging based regions, but these are the few important regions we find out by talking with the radiologist at MD Anderson Cancer Center, and also in literature, that they may miss it because due to the missed fixation, either they have never looked at the abnormality. Reduced fixation duration, which is fixation is the amount of time, the you can see these red dots are fixation, which basically the eye gaze data. So reduced fixation is basically they have less attention, look but not for long enough to process the findings. So if you see, I show here the teacher's data, radiologist, one of the experienced radiologist data, and the student side is basically data from the, I can say, inexperienced or student data, where you can see he misses the right effusion, and that is happens specifically due to the missing fixation durations or less. So and there can be third region of the error, that the student has focused every region and and focused enough as well, but just that he doesn't understand the patterns of the error. So because we want to develop again, we want to develop the education system which can give a personalized feedback about their errors, what they miss, what they not miss. So we just don't have to tell them what you missed, but we also need to tell them why you missed, so that they can go and correct it. So we need to develop like a dual system which can detect the abnormality, but detect the missing abnormality, but also create make the give the reason why they miss it. Is there any question? I think I see a hand raised. Please let me know if there is any question.
I don't think so right now.
Okay.
I don't
All
see
right.
a hand raised here.
Oh, I just noticed. Anyways, okay. So now how we can develop those kind of systems which can give the the reasoning behind why the error happens, right? So definitely the best thing here to do is that can we use current LLMs to do this reasoning, okay? Because LLM and LMMs has the power to do the reasoning on the even on the multimodal data. But what we found is that if we basically use LLMs and LMMs to compare the student and teacher data, we see that if you see in the figure A, there are three regions we consider for the perceptual error: missed fixation, reduced fixation, incomplete knowledge, or no missing abnormality. And we give the student and teacher data to an LLM or LMM and ask it to compare these two data set, the pair. You can see that under the current prompting strategies or conventional prompting strategies, model gets confused. You can see ZSCOT is zero shot chain of thought, and FSCOT is few shot chain of thought. GT is the ground truth. Like for this case, the missing abnormality, the abnormality is missed is left diffusion. And why it is missed? It is missed because the fixation points are less. They're not much fixation, which means that the student has not basically explored this area for didn't explore much. So you can see that under the current prompting strategies, LMMs can compare, but they are not able to give the label is not right, because it's very the gaze data and student report, and currently we give the student report and the student gaze and teacher report and teacher gaze and ask it to compare those, and it's hard to really do this multimodal kind of a reasoning because gaze data is pretty big. A lot of fixation points. So you can see here that the current prompting strategies, LLMs, cannot really do the deep reasoning across these two multimodal signals, student and teacher. So to basically enable that, the reasoning capability of the LLMs, to increase the reasoning capability of the LLMs, we proposed a new prompting strategy, which is called SCoT, which can take the gauge data, and the report in a structured format, and can reason between the student and teacher data and can give a personalized feedback. Because we want LLM or LMM or any large model to compare these two multimodal signals, and under the but due to the heavy prompt, the model gets confused in comparison, because it's like a very, very subtle differences. Like comparing just this part there's a difference in the number of fixation point. It has to really region in the deep. So it doesn't happen with the current prompting strategy. So we have to come up with something new so that it can do this deep reasoning. How this SCoT works? SCoT is basically based on two important concepts called structure generation and prior generation. So there are two important pillars of SCoT, that rather than prompting structure of the data and then also create some prior with that. So what we do here is that we take the student gauge data and teacher gauge data, and we create so you can see this is the DT, it represents the teacher data, and this is like we create a scene graph with that. We basically say thought graph, but using the student gauge data and student report, we create DS, which is a thought graph. I'm going to show you how this graph look like, but we basically create a structure. And that structure can change if the domain is different. Like if it's another kind of an education platform, we want to develop it, then you may change the structure. But basically, rather than dumping all of the data in the prompt, it's better to create a nice structure of it. This is a multimodal structure where each dot represent the fixation points, and also we also infuse the diagnosis in this graph, and I'm going to show you how does that work. We create the structure. We say here is a thought graph generator, and then we have a structured discrepancy operator, which is nothing but generating the prior, because it's really hard for LLM to reason on this deep region on this bigger prompt. So we also generate some prior using this structure by and we call it a discrepancy operator, which is nothing but just taking the graph difference between the GT, the student and teacher graph. We just take the difference, and that we pass it to as a prompt to the LLM and ask it to tell that why, if there is any error in this, compare these two graphs and tell if there's anything missing. So just this kind of prompting strategy enables LLM to do a deep reasoning because of the the nice structure and the prior we present to the LLM. So how our prompt looks like, if you see that, this is the graph. This is how we generate the graph. This is a thought graph we create. So you can see that if there is a radiology report saying like 4 abnormalities, so we will be having 4 subgraphs, right? Each subgraph representing one thought in the report. So like you can see, this is one of the subgraph related to moderate cardiomegaly. So student may go to the heart. This represents specifically the heart region, and each node represents the gauge data, and the edges represent how we navigated for the cardiomegaly. And lung capacity will have its own subgraph with the nodes and the edges representing basically the order of the fixation. And there is an ideal subgraph, which is sometimes radiologists just don't say anything. They just look at the abnormalities because they're just thinking. So that's, we say it as idle subgraph. So we can see we create this thought graphs for student and teacher both. And this is basically used as a prompt in the SCoT. So you can see this is the prompt for the SCoT. You can see we in the prompt we have we input these graph as a scene graph one, experience and inexperience is basically a student, and then we also infuse the prior, which we generated. You can see these are the priors we generated from the structure using the structure discrepancy operator, which is nothing but taking the difference of these two subgraphs to tell that if there is any subgraph is missing in the student data, and if there is any missing, then what are the fixation points missing. So it's like just taking the graph difference operator, and then we infuse it all to the, and then we ask a question based on these observations, and your task is to return a JSON object with following answers. So like we make it because we are trying to test the reasoning capability of the LLM or LMM, and we don't really have a like specific metric to do that. Either we can just compare NLG matrices. We don't want to compare the NLG matrices. We wanted to see that can it really reason. So we asked some questions. We infused some questions in the prompt asking that, okay, based on the comparison and all these reasoning, can you tell why, if there is any missing if there is any missing subgraph or missing subgraph due to missing fixation. So we make it as like a multi-label classification problem at the end, because LLM has to answer based on all this reasoning it does on this data, and with the prior it has to answer that these as a 0 or 1. So we, for each multimodal pair, we get 0 or 1 as a the answer, because it may be many different regions for a particular abnormality to be missed. So the important part here is that there's no data set exists to evaluate this kind of prompting strategy or evaluate this kind of method. So what we do is we create a simulated error data set using the EGDCXR data. That's an eye gauge data having 1083 chest x-rays synchronized with eye tracking reports. What we do is we synthesize the perceptual errors in this EGDCXR data by masking some of the abnormalities and also the corresponding gauge data. So that's we call as a missing fixation. What we do is we mask out some of the gauge points, we mask out some abnormalities and also corresponding gauge points to simulate the region of missing fixation. For some of the abnormalities which we mask, we correspondingly reduce the fixation durations to simulate the region of reduced fixation duration. And another region is basically incomplete knowledge, where we just remove the report, the abnormalities randomly, and don't do anything with the gauge data, because we want to simulate that biologists have most of the thing, explored the whole region, but didn't have the capability to recognize the pattern. So, and then we also simulate some errors, like with no errors. Some of the samples are with no errors. So you can see this is the distribution of the data with different samples we produce. So let's go back. So this is the data we have a simulated error data set created here for evaluating this kind of a system. And then the baseline we use to evaluate our SCoT is the 0-shot chain of thought and few-shot chain of thought methods of prompting we use as a baseline. The models we use for evaluation is Llama, Mistral, GPT-4, because from a smaller model to bigger model, we wanted to also test the smaller model and also a little bigger model to test that how well it does. And then we frame it as a multi-level classification problem. Because it's a multi-level classification problem, we use accuracy, subset accuracy, macro precision, recall F1 score for evaluating the performance of the methodology. So if you see that the best, you can see the evaluation matrix here across Mistral, which is the smaller model, SCoT, that 0-shot SCoT performs pretty well compared to the other baseline FSCOT and ZSCOT. So you can see that because which means that structure and prior really helps in doing the deep reasoning between two multimodal data. And Llama also, and also across the GPT-4o, we get a better performance for using this SCOT prompting technique. So performance gains are observed across model sizes for smaller model to LLMs. As you can see that the larger model basically benefit a little more. And the class-wise performance also we show here that you can see the model, our ZSCOT, has a better performances across all the different classes. I show this for GPT-4o only model, but you can see that it gains the performance across all different classes. As you can see, there are four different classes specifically: missing fixation, reduced fixation, and incomplete knowledge. The difficult class to determine is an incomplete knowledge, because it's a long context problem then, because it has to first see if there is anything missing. If not, then is there any fixation points are reduced? If not, then it means that something might go in this category. So it has to really maintain the context to really determine this incomplete knowledge class. So that's why you might see a little low performance for this particular class because of the long context. LLMs still people are working on it, but SCOT still helps a bit in the long context issue. We also tested the other baselines with SCOT, like across different other models using graph of thoughts and tree of thoughts as well. And you can see that across all models, our SCOT outperforms. And that's very useful because the journal reviewers has asked us to test, and definitely because these prompting techniques are developed for the multi-path reasoning. Then I want to show some quantitative results actually here. If you see in the Q1 different if you see in the Q1 subblock, there are two student and teacher data, and we have like 4 classes. As I told you, missing MF is missed fixation, RF is reduced fixation, IK is incomplete knowledge, and MA is no missed abnormality. So the model does pretty well compared to, it can tell the region why it is missing compared to the different other classes. This is the important part here. I show that what kind of personalized feedback we can produce using this technology, using this kind of SCOT. So you can develop a system which can take the student and corresponding teacher data, because it's like a comparison, but it can also enable a personalized teaching and personalized learning. Because the model is, we can use LLM to give a personalized feedback, because we infuse the gauge data, but student can also select the teacher whom they want to learn from. So it's like a personalized teaching and personalized learning it enables. And you can see that so for this particular pair, the student has missed this abnormality of fluid on the below region, and then is due to the missing fixation. And model can do this reasoning and tell that why this is missing, because this has these points missing. So which helps actually radiologists, senior radiologists, to teach their teach their residents, because now you can give very detailed feedback that why you missed this abnormality. So we also do the response time comparison analysis. If you see that the SCOT has a bit of a little more response time compared to the ZSCOT and FSCOT, which is definitely due to the multimodal reasoning it has to do. Graph reasoning, multimodal graph reasoning it has to do. That's why a little bit higher. But I think these ZSCOT, FSCOT has a very low accuracy you've seen, which is better than having a little more a response time. So which is get like a 6.48 seconds to produce the output. So this paper was published in a knowledge-based systems journal, and was one of the top recent downloads as well. So one of the important thing you have noticed in SCOT, we can develop agents using SCOT, single agent systems, but The important thing which you have noticed was the prior. I mean, some of you might be thinking that it incorporates a lot of domain specific priors, right? Which is hard to think about what kind of priors I'm going to infuse for a different kind of pathology, maybe education system. Then you might have to think about the prior, which is very domain specific. So SCOT, which I presented, is more like a spoon feeding, which spoon feeding the LLM, which reduces its generalizability. So how can we do this? What can we do so that we can reduce the be independent from this prior thing? So one of the important thing, if you see here, is in student and teacher data, the length of the data, the length of the eye gauge data, it's pretty big. So if you give all these data to the single agent, I have shown you in FSCOT and ZSCOT of the baseline, the model was not able to do a deep reasoning and was confused in finding why the error happens between the student and teacher data, because it's really a big prompt, which is like confusing. It's like a big prompt for the model. So can we eliminate this? And to handle this big prompt, we have to like a spoon feed it. Can we eliminate this prior dependency? Can we divide this task of bigger analyzing this bigger data among multiple agents? Can we just not have a single LLM looking at this big data? Can we have multiple people, multiple agents together working and looking at the different subparts of the data and further finally analyzing the output and giving the answer? Can we do this? If we can do this, then we will not, we may reduce the dependency on the prior, because the prior we needed in SCOT because of this long eye gauge data and model was confused. So if we can develop such type of multi-agentic system to give a personalized feedback to radiology student, what are the things we need to take care of? First of all, how many agents are we going to need for this analysis? Okay. And then another question which we will be asking is, how much can we like scale these number of agents based on the complexity of the perceptual errors, right? Because you can bring in so many agents, but sometimes you may not need that many agents to find the why student make the error, because student might have just made one error and you are bringing so many agents to analyze its error, which may reduce the the efficiency of the system. So can we have an adaptive number of agents for solving this for analyzing this complex multimodal signals, right? Can we dynamically adjust this number of agents for analyzing the multimodal student and teacher data and give the feedback why they miss it, and also remove the dependency on the prior? So for this, how did we do it? We developed a new basically agentic system, which is basically based on we take the same concept of thought graphs from the previous the methodology, and these thought graphs are constructed the same way as I described, but we define an error complexity and agent allocation function, which is like taking the difference between, first we find the missed abnormality, number of missed abnormality, and then scale the number of agents based on the missed abnormality. So first we find the number of missed abnormality, and then we scale it based on the number of fixation points in the for the missing subgraph, which will tell that how many errors the student made and how complex those errors were. Because if like he's making 4 errors, then we need like 4 agents to analyze analyze the student and teacher data. So we scale the number of agents, not just 4, we also multiply with the subgraph needed to for the comparison. So number of agents is a function of the error complexity, which is, an error complexity is nothing but the product of the number of difference in subgraph counts and the difference in the the number of fixation points for that missed subgraphs. So the MAARTA, the technology, the methodology we developed is MAARTA. We name it as a MAARTA. It's a multi-agentic adaptive radiology teaching assistant. Actually, it's a multi-adaptive, basically adaptive agentic system, where you can see that it takes the thought graph. Thought graph generator generates the thought graphs. Right, I presented the thought graph, and then we have three main types of agents here. Principal agent, principal LLM, which is going to take the thought graphs and find the missed findings. And then we have an error complexity calculation module, which is going to calculate how many agents we need to really compare these two data sets, these two multimodal signals. So you can see that because this principal LLM is just going to compare the report and tell what is missed. And then error complexity function is going to use that number of missed finding and then scale it based on the subgraph complexity of the missed finding and then find the number of agents. So you can see that here there are many agents we recruit for analyzing these two thought graphs. And then each agent may look at the different parts of the data, right? Different subparts of the data, and for each missed finding. So for each missed finding, we may have multiple agents looking at it based on the complexity. Because if lung opacity is missed and it was like a very hard to find the lung opacity for a teacher itself, which means that it is a complex error. So then we need more people to analyze that particular error. So these agents works in parallel, and then they analyze the different subparts of the data, and then it comes to the consolidator LLM, and they give their output, and then it finds the final reasoning of why the student missed it. So you can see here we remove the dependency of any prior so that we can make it more independent and generalizable systems.
Hey, Akash. Hi, Pulkit here. Sorry to interrupt. I thought it would be nice to interact a bit and get some questions so that it gives you a break as well. So I don't see questions in the chat, but I'm already very much enjoying the talk. It's something very new to me. So I had a couple of questions. One pertaining to the slide that you have right now. So you mentioned a couple of times that these agents, they look at different parts of the reports or of the graphs. I wonder how that is determined, like what different things are they looking at the graph? How do they complete the information? What do you mean exactly when you say that they're looking at different parts of the system to give a final answer? Yeah. And my second question would be, have you only talked about like using those key points and creating a thought graph generator. Do you also directly use the imaging data in the model?
Yeah.
Yeah.
Yeah. So for sure, answering your first question about the subparts of data is basically so you can see that the thought graph is multiple subgraphs, and each subgraph represents one thought, and that's one abnormality. So let's consider this particular one age. So let's consider lung opacity is missed, and then so there will be a subgraph for lung opacity, and then we have to so this particular agent is going to compare the lung opacity subgraph with the student subgraph, because student graphs has also multiple subgraphs, and that lung opacity subgraph is missing in the teacher's one. So it is going to compare the student graph with the teacher's subgraph that why this happens. Is it something that there is no fixation corresponding to the lung opacity subgraph? Is it the fixation that he doesn't have on those regions, or it's due to the reduced duration, or it's just that all the points exist but there is no it's just due to the third region, which is incomplete knowledge. So it's like not completely each. Now you can see the amount of data this particular agent is going to analyze is less than the SCoT used to. SCoT used to take the both bigger graphs containing many subgraphs and then do the reasoning. Now this agent just compare for a particular abnormality lung opacity in the student graph and see that because so let's consider the lung opacity is missed, and then we have five subgraphs in the student data, right? So it is going to compare the lung opacity subgraph of a teacher with all the five subgraph present in the student one, right? So that's why like a parallel agent, number of parallel agents working together, for each abnormality. Did you get the answer for the first question? It is a little complicated, but I'm happy to answer if you don't understand that.
Oh, that was clear. Yeah.
Okay, yeah. Sorry, it's a little. So basically, yeah, it's more of a adaptiveness of number of abnormalities and also the complexity of each abnormality. Because if you have four abnormalities, then you will have four these rows, and each row will have the number of agents based on how complex that particular missed finding is. If student is very much have so many subgraphs to compare with, then we will have like many agents to check whether what's the region. So you can see the number of data reduced. Second question was about your second question was about whether we're just trying to input the imaging data. We don't use image in any of those methodologies as SCoT and MAARTA. Most of them are based on the gaze and report. That's the one thing that, because we don't want to have any kind of pre-trained model coming in and infusing its trained image feature based knowledge, because we want to have it more based on the reasoning part or giving a feedback rather than infusing AI models knowledge, which we don't know what kind of data it's trained on. But yeah, now there are more models we might use, but currently we don't use any imaging, the real image pixels or medical features in this feedback generation.
Okay. Thanks for the answers. I think there's a question in the Q&A if you wanna take that, read that aloud and answer.
Right, let me see. Okay, where I see. There's a question. Oh, I don't see the question. Can you read it for me, anyone?
Okay. I think it's in the Q&A box. I can just read it for you.
Oh yeah.
The question is, how do you align each miss of the student to their subgraphs?
How do you align each student to their subgraph? Okay.
Each,
So
I think that each miss of the student, I guess the missing part of the report to their subgraphs.
okay. So yeah, we have the transcription, report transcription, and the gaze fixations, and the fixation durations. So I know that's a very good question. There can be a little misalignment between the gaze, because these are two time series. There can be a little misalignment, and there is sometimes misalignment happens, but we work on that assumption that there is no misalignment. But yeah, it may there is always a misalignment between little bit misalignment between student and teacher. But we did when we created a subgraphs based on this eye gaze and the transcription we have discussed with the radiologist. Many times it looks good. The graph looks good based on the user study we did. But yeah, we use those time points of gauge and report to synchronize. We consider them synchronized, but they may not be.
Yeah.
Whether does that answer the question?
I assume so. Okay. If there are follow-up questions, please feel free to type them in. Okay. Yeah.
All right. Can I go
Yeah.
quick? Okay. So again, the same models were tested as we have seen in SCoT with the zero shot prompting. Actually, each agent used the zero shot prompting, and we use the AutoGen framework to develop this develop this methodology. So yeah, there was a Bulkit's question, very nice, good question that yeah, we don't use the imaging data anywhere here, but we do input only the gaze and report using just one agent. So you can see that it's pretty low. The performance is low. It gets confused in determining the region of the error. We also did an ablation with single agent with thought graph. It does, I mean, the performance basically goes down. But when we use the MAARTA, which is multiple agents with thought graphs, the performance basically increases here across all three models, to smaller to larger, which means that the LLMs still struggle with doing the graph reasoning. And there has been a papers about that LLMs struggle with the graph-based reasoning or multimodal graph reasoning. So this having multiple agentic systems, looking at different parts of data really helps increasing the subtle reasoning increasing the reasoning capability of those models when there is subtle differences between the multimodal data. So we show some the results here. MAARTA demonstrate the ability to reason over the complex case, and you can see that this is the student data, teacher data, and model can tell that the missing fixation is the region of this. There's a bilateral effusion, and it tells that it happens due to the missing fixation, and you can see this T-student fixations are missing here. We also did the, you can see the graph here. As you can see, as the performance, as the number of agents increases, the performance of this is having loss here, the performance decrease basically increases. So when you have more agents, for some time the number of agents increases, the performance also gets better for most of the model, but it also depends on the type of and capability of the model. So this was our paper in MICCAI. We also, as I said, we also developed the whole web page, the web-based system to do this radiology-based teaching system, which can give a personalized feedback, and it runs SCoT in the backend to give the personalized feedback to the student. So our system looks like this. You can upload the cases, and it can generate the whole dashboard for the student to tell that what they missed, and also give a personalized, like some learning opportunities to that, like, hey, you missed this part, and reasoning is based on their gauge specifically. So I mean, this website is going to be released by the RSNA soon. Basically, RSNA will release this website. We will be in the news, so this website will be released by the Radiology Society of North America in December, and then people can start using it. So we also did some user study with this system, actually, at MD Anderson Cancer Center. And then, I mean, radiologists pretty much like the idea of using this kind of system for teaching. We do have an accuracy of a dashboard a little low, and we are working on it to increase, because when it goes to real time, there will be a very noisy gaze and all of that. So future plan is to extend its system for CT, MRIs, and everything, and also do more clinical work studies, go to the hospitals and check it. How does it work? Extend it for pathology and other, other domains. And yeah, this is our nice team who works hard to develop those systems from MD Anderson and from University of Houston, University of Arkansas. Um, so yeah, thank you for listening. I'm happy to have more questions, and you can always contact me on my email there.
Yeah. Thanks a lot, Akash. That was a great talk. Very insightful. Yeah. Um, Let me check if there are any questions. Doesn't look like it. If someone has any final questions, you can also raise your hand if you want to speak. We can unmute you. Just give it a couple of minutes.
Sure.
Yeah. I have a lot of questions, but in the interest of time, maybe I can ask one more and pick your brain about it. So, remind me, like the number of training cases you have were around 1,500, I think. Um,
Training cases. So we have not done any fine tuning or anything in this. Those were the error data we created, and everything is based on the inference
interesting.
time
Okay.
or test time scaling.
Yeah. So you directly do the inference on these already
Yeah,
open
yeah,
source trained models.
right.
So yeah, have you thought about doing any fine tuning on any of the LLMs, or creating your own version of that, especially just trained on
Mhm.
vast amount of radiology reports?
So we are working with Stanford now, actually with one person to create those kind of, because there is no error data. It's really hard to get any error data to really train those models. We are working with the people there to see if we can you know uh, get this kind of any student error data, but we plan to also you know work on more side of like fine tuning the prompt, like the prompting, text grad based approach, because we have seen this, the performance of the reasoning performance is very much dependent on the prompt words. So we plan to maybe prompt fine tuning we might do, but really training or fine tuning it on error data that there's no error data exists. If we just simulate and we fine tune it, what it knows also, that due to catastrophic forgetting it may also get worse. So we just wanna, and also then we limit the use of the system, because we just want to have it like people can use it without any lot of compute, and we just do an inference. So that's also one reason in clinical the time is important.
Yeah, 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 that makes sense. Yeah. Uh, so what are your, I know you talked about uh, you're gonna apply this to other pathology domains.
Mhm.
Um, and I was just wondering, um, have you thought about at what stage of a radiologist's training, like resident training, you might see different kinds of errors appear throughout the training of like XYZ number of years, and cater the education to that particular residency year, or something like that. I don't know.
So as the number of experience grows,
Mm,
the possibility of error goes down. So we design this system specifically for the medical students
mm,
and the starting year of the radiologist, because then you can see number of errors and all the scaling. This scaling thing will really work with the medical students like first year, second year, and those trainees. It will work well because of this scaling of MAARTA specifically. So yeah, it's for medical students, I should say, it's very useful. I mean, as a, the experienced radiologist is really not make that much error. It's like a very heavy tail distribution for them.
Yeah. Thanks for all the questions and answers. I don't see any questions in the chat box, but I think it was a really great talk, and it was something very new to me. So it was a great learning experience. And yeah, if you have any closing remarks or anything you want to add.
Sure, sure. So thank you so much, everybody, for joining in this talk. And if you have any questions, my email I can just put in here. We are always happy to answer these questions. You can email me, and we do have the we will release our one website. I mean, RSNA will release it in December, and then you guys are welcome to come in. I'll share the link with the MICCAI people if you guys want to share that as well for RSNA. I'll be happy to answer more questions and use our website. Thank
Yeah.
you.
Thank you. Thanks again, Akash, for volunteering to speak, and thanks everyone again for attending the session. Cool. Happy Saturday, and
Happy Saturday.
yeah, thanks.
Bye-bye.
Bye. Like,
Bye.